All right, we have a little bit more to go with our potential energy diagrams. And where we need to start is I want to go back over these, and I'm going to ask the question, which of these two diagrams do you think would result in a higher reaction rate? Which one of these reactions would go faster to the end? All right, well, it's going to be this one here because it has this lower hill to climb. The lower the activation energy, generally the faster the reaction rate. And so if that's the case, then we want to do some things that are either, if we want to make a reaction go faster, or go slower for that matter, if we want it to go faster, we're going to have to do some things to our reactants to either give them enough energy to get them over this hill, okay, or, it's either you can go to the mountain or you can bring the mountain to you. And in this case, we could actually, what circumstances can we actually drop the activation energy and allow a reaction to go faster in that regard? So we're going to shift gears a little bit, and I want to give you something else to keep an eye on. Okay, so we're going to start with the idea of this, and we've seen this before, and I've shown you this concept before. We're going to zoom out a little bit. Let's come out here. Okay, and so we have this idea of what's going to happen is any point on this graph is going to give us the number of molecules that have a particular amount of kinetic energy. And generally when we do this, we will generate a curve that looks something like this, where we get this nice bell-shaped curve. And right in here, on this line, this is where we have the average kinetic energy of all the molecules. Now, we've talked about this before. We've established what the average kinetic energy of molecules is. And this is temperature. Okay, the idea that we have all these range of molecules, but our temperature is given by the average kinetic energy of all these molecules. We may have molecules moving faster, we have molecules moving slower, but this is the average of all of them. Okay, so I may tell you, then I'm going to bring this into play. And this black line right here represents the activation energy of a reaction. And that you have to have molecules with, where's that pen? You have to have molecules with energy that is beyond this line. So molecules that are out here will be able to react, and it's only those highest energy molecules. So something we could do in order to make more molecules go beyond the activation energy is if we moved our temperature and we were able to raise the temperature to, okay, so that we had more molecules actually occurring beyond the activation energy. Okay. However, this doesn't always work, and sometimes it's impossible to raise the temperature of something enough to actually make the reaction go. Okay, so we may have to come up with something else, and there's another factor that increases reaction rate, and that was increasing the concentration. And so if we increase the concentration of something, what that's doing is it's increasing the number of molecules. Oh, I only want to move this. So if we increase the number of molecules, we have more molecules fitting beyond the curve, but that really doesn't do us a whole lot of good if if the activation energy is so high that our molecules just can't do it. So is there a way to bring the mountain back to us? Can we get this activation energy lowered so that our reaction will occur with molecules that just have an average temperature. All right, and there is a way of doing this, and the way we do it, well, before we get to that, there's an example of something, and you guys have learned this in your biology class. There's an example of a reaction that has a very, very high activation energy, and it's this equation. Okay, and you've seen this before. This is glucose. This is oxygen, carbon dioxide, and water. Now, we see carbon dioxide and water in the same place all the time. In your soda, we have carbon dioxide and water, but you never ever see it produce its own glucose for a sweetener. You can't just put carbon dioxide and water and make it happen on its own, although those are the components for it. There needs to be something that causes this reaction to go. Now, this reaction is called photosynthesis. And photosynthesis has a very specific thing that helps this reaction go when it wouldn't normally happen. And that stuff is called chlorophyll. This chlorophyll comes over here to this ridiculously high activation energy, and it lowers it. In fact, it lowers it so low that you just need a tiny bit extra energy to make this reaction go. And that tiny amount of energy actually happens to be sunlight. Okay, so that light comes in, and this amount of energy to get from here to here, that tiny amount, comes from just sunlight hitting the reaction, and is able to turn the sunlight into our glucose. Because this chlorophyll is able to drop our activation energy so far. When you have a chemical that is capable of decreasing the activation energy on its own, all it does is decrease the activation energy. It is called a catalyst. It is called a catalyst, and that is what lowers the activation energy. Of a reaction. So, let's say that we get, in this reaction before, there was enough sunlight to give us enough energy to get here. Okay, well, it would not be enough to reach this activation energy, but it's plenty to reach this activation energy, and that's how the catalyst takes advantage, and that allows molecules with a moderate amount of energy, more than just sitting there, but not nearly enough for this activation energy to actually allow the reaction to go. Now, there are certain molecules that can come in and will actually counteract a catalyst, and they only occur when a catalyst is being counteracted. Okay, and we have this a lot in biological systems, where because most of our biological reactions occur under the existence of a catalyst, or an enzyme, is what we have as a biological catalyst. We will sometimes need something that will stop a reaction, and so what that does is it actually increases an activation energy, and this is called an inhibitor. All right, so a catalyst will reduce an activation energy. An inhibitor will block it will actually block a catalyst from doing its job, and will raise the activation energy, making it harder for the reaction to go, and slow it way down so it doesn't run away. And a lot of times we don't want to have runaway chemical reactions in our body. Okay, so that is the idea for catalysts and inhibitors and how it relates to our potential energy diagrams. And that is all we needed to cover for today.